ago yesterday that a stranger came to town. The tell me he's a stranger young that shot around.
This is going to be an explanation of a parallel inductor resistor circuit. On the right hand side we have the circuit. We have a 100 millihenry inductor in parallel with a 1 k ohm resistor in parallel with a voltage source of 5 volts RMS with a frequency of 2 kilohertz and a 0-degree phase. It doesn't matter how you express the output voltage, whether it's peak voltages, peak to peak, or RMS, as long as you maintain a consistency throughout. So on the left, as you can see, the first thing you do is you find, using the inductive reactance formula of 2 pi FL, you plug in your values for the F, frequency, and L of inductance, and you get a 1.257 k ohms. Now, why do you need to do that? Well, so then you divide that ohmic value into the 5 volts RMS, and you get 3.979 milliamps, and there should be RMS here. I got this out of a book, and they didn't exactly put the RMS here, but if it was in peak voltages, then this would be 3.979 milliamps peak, or if this was in peak to peak, it would be 3.979 milliamps peak to peak. But because this is RMS, then the value is 3.979 milliamps RMS. And you do the same thing for the resistor, and you get 5 milliamps RMS. The RMS is missing here as well. Now, when you look at this, you say, well, I got 5 milliamps going through a resistor and 3.979 milliamps going through inductor. So I'll just add those up, and that's the total current flow into the parallel branch from this voltage source. Well, that's not correct. What you have to do is you take the individual currents, and using Pythagorean theorem, you plug it in. The 5 milliamps and the 3.979 milliamps are the sides of a right triangle. The hypotenuse is the total current. And so you plug in those values into Pythagorean theorem, and you end up with 6.39 milliamps RMS. And it's rather interesting that the current that you end up with and the current, which is the same as the current coming out of this voltage source, is actually less than if you were to add the 5 milliamps and the 3.979 milliamps. That's just an interesting aspect of electronics. Now, why do you need to know the total current? Well, because you take the total current and you divide it by this 5 volts RMS using Ohm's law, and you get the equivalent impedance. The equivalent impedance is important because this circuit in and of itself is rather useless. It's like a potted plant just sitting there doing nothing. It means nothing. It's doing nothing. But if this is a load to a previous circuit, then the impedance is important. You need to know the impedance so that you can match that impedance. Or there could be a load attached to this, and thus you would need to know the impedance as well. So in and of itself, it's not that important, but if there were, it's not being shown here, but there is no real load attached to this, and it's not indicated whether or not this is a load. So this is just an exercise. And the circuit in and of itself is rather useless, doesn't do anything. But the important aspect of all this, the one difference here is, and the one thing that we have to find is the relationship between the currents, or the currents through the inductor and the current through the resistor. Because the voltages are the same, they're both in parallel. The voltage across the inductor is the same as the voltage across the resistor. But what about the current? Well, and so that's what they're trying to show here in this book. I got this out of a book. And it's interesting, they use the fourth quadrant. This is an XY coordinate. Along here is the x-axis, and up along here, the vertical, is the y-axis. And so they're using the fourth quadrant to explain how it is they derive, and here's the angle that they're trying to find. They don't show it. This is a very minimalistic representation or diagram. But here they've got the formula, and the whole point of this is to figure out the angle. How do you find the angle? Well, because this is rather skimpy and it's not all that, doesn't show a lot, I came up with my own graph, and here's my graph. And so my graph shows how you find the current relationship between the resistor and the inductor using the first quadrant. This right here represents the first quadrant. Now, on the horizontal axis, this whole thing is an XY coordinate that you see in algebra and trigonometry. The horizontal axis is the x-axis. It's also the adjacent to this angle. This right here, this blue vertical line, is the side of the triangle that's opposite this angle. And so when you divide the length of this side, the opposite, divide that by the horizontal axis, the adjacent, you plug in whatever that value is, and you take the arctangent of it, and you get the phasing. So that's essentially what this is showing. Now, notice that the horizontal axis is also indicative. It represents the resistor. It represents also the voltage across the resistor and the current through the resistor. They're all in phase with one another. And not only that, but the voltage across the inductor is represented by the horizontal axis. Now, why is that the case? Because the voltage is also the same voltage is applied across the inductor and the resistor. This is a parallel circuit. So the current is the sort of the odd man out. It's going to be the thing that's not in relation to the voltage. So this horizontal axis represents, as you can see here, because this is a parallel circuit, this also represents the voltage across the inductor. Now, if you jump over to here, this mnemonic, this is a very important mnemonic that one should commit to memory, and it's called Eli the Iceman. And what it means is that for a series circuit only, the voltage leads the current in an inductor. That's what the word Eli means. The ice or Iceman, ice, says that the current leads the voltage in a capacitor. So somebody came up with this mnemonic, Eli the Iceman, to remember the relationship between a voltage and a current in an inductor circuit and a current versus a voltage in a capacitive circuit. However, this only relates to a series circuit, and as you can see, we do not have a series circuit. So we can't really use Eli the Iceman because it represents a series circuit. So in order to get the mnemonic right and to represent a parallel circuit, you just simply reverse the I and the E's. And so instead of Eli the Iceman for a series circuit, we have ILE and ECI in a parallel circuit. And so what this is saying is the current leads the voltage in an inductor, and the voltage leads the current in a capacitor. Now since we don't have a capacitor, then all we need to use is this. So what this is saying is that the current leads the voltage in an inductor, and that's what I'm showing right here. The black represents both the voltage across the resistor and the voltage across the inductor, because they're in phase, and they're in phase because they're in parallel. But what this is saying is that the current leads the voltage in an inductor. So here's the current. So at 0 degrees, when the signal starts moving and it's going in the counterclockwise direction, it's going through quadrant 1, then through quadrant 2, quadrant 3, and then quadrant 4. And in going in the counterclockwise direction in relationship to a sine wave, and this represents that 2 kilohertz sine wave, you start out at 0 degrees, and you're going in the counterclockwise direction, you're going like this. So to go from 0 degrees through 90, through 180, back to 360 degrees, one cycle, is the same as starting at 0 degrees on an XY coordinate and going counterclockwise through 90, through 180 to 270, back to 360 degrees. So at the 0 degree point, when when the signal is just starting out at 0 degrees, notice the current is already at 90 degrees. It has a head start. It has a jump on the voltage. And so this blue is the vertical axis. It represents the angle. So this blue is at 90 degrees with the voltage of an inductor. So the horizontal axis, the green, represents the voltage of an inductor, whereas the blue represents the 90 degrees of the current which leads the voltage in an inductive circuit. And the resultant, the hypotenuse here, takes into consideration both the resistance and the inductance. So then ultimately, to find the angle, and you don't have to have a background in trigonometry, you just have all you need is a calculator that has a tangent, and thus it will have a arctangent. You plug in the length of the opposite side, divide that by the adjacent. Now, what are the values of the opposite side, this blue? What is the length of this and the length of the green? Well, it's right here. This, the blue represents the current through an inductor. So that would represent 3.979 milliamps RMS. And the horizontal axis, the current, which represents the current through a resistor, is the length of that, if you want to call it that, is 5 milliamps RMS. So you take your 3.979 milliamps, divide into that 5 milliamps, and you come over here, and that's the opposite over the adjacent, and you get 38.512 degrees using the given values. And so that's how you find the angle that's associated with this circuit, which is very important. So once again, and also note that the vertical axis, the blue, is in the XY coordinate represents the y-axis. It represents the opposite, the current, and it represents the current through an inductor. So this is sort of a chart that shows in detail how you derive the relationship between current and voltage and the angle and the XY coordinate as it relates to a sine wave. Going along, and this is I'm not showing it here, but the horizontal axis in the green also represents the time. It's in the time domain.